All right. Good morning. We're going to be talking about conditional probability today, and hopefully we can get through that somewhat quickly because I'd like to go into expected value. That way we leave Monday open for a little bit more difficult of a concept. So what conditional probability is the probability that some event is already happened. It's given. So you know that we only are looking at a subset of our sample space where you've already been given a given condition, and then we want to look at that probability inside of that given condition. So you probably have seen the notation before in geometry, but this little vertical line is basically saying this is the probability of A given B has occurred, or given B is going to occur, so forth and so on. And there's a couple ways that you can do conditional probability, but probably the most straightforward way is with the formula. So it is the probability that A and B have occurred over the probability of B. So the best way to kind of understand this is we're going to look back at that example about the cookie jar from the last lecture, and that way you can kind of see how all these pieces are coming into play and what this actually kind of does. So again, so if it was swapped, so if this was the probability of B given A, hopefully you all can switch things up. This is still the probability of A and B happening, but now over the probability of A. So whichever one is the given is going to be your denominator, because we're basically, what we're doing is we're making our sample space into that subspace of the given probability. So we're only looking at that as being our total probability now. So this is what this is going to do. So let's look at a couple examples. So again, let's go back to that cookie jar. So I'm going to make the tree that we did, so we can use that again. So we have jar A, we had jar B, so there was 1/2 probability on both of these. Then for chocolate chip there were 2 out of 4, and for peanut butter there were 2 out of 4 as well. So with jar B though, there's only 1 chocolate chip over 1. So we can look at all of these total probabilities. So this was 1/2, this was 1/4, and this was also 1/4. Okay. So again, you can see that these all add up to 1, so these were our total probabilities from that last example from last lecture. So this time, though, we are going to ask the question, given that it is a chocolate chip cookie, so we are given that it was a chocolate chip cookie, so that means that we pulled out a chocolate chip cookie. We now want to know what the probability was that it came from A. So we could write this into its format. So this would be the probability of it coming from jar A given that it was a chocolate chip cookie. So my equation is going to be the probability that it came from jar A and it was a chocolate chip cookie over the probability that it was a chocolate chip cookie. So we can go and look back at this chart. So we saw last class we actually did the probability of a chocolate chip cookie. So we had this 1/4, but we also had this 1/2, so we added those two things together. So the probability of a chocolate chip cookie was equal to that 1/4 plus that 1/2, which gives us that 3/4 probability for it to be a chocolate chip. So we now know our denominator is 3/4. So now I want to look at the probability that it came from jar A and it was a chocolate chip. We already did that math as well. So all I have to do is follow the actual lines to go to where it was both jar A and it was chocolate chip, and that was a 1/4 probability. So that means that this is 1/4. So we can go and reduce this math and we get out 1/3. So there was a 1/3 chance that us picking a chocolate chip came from jar A. So that was our answer right there. So again, we had a nice setup going. So then I was given that it was chocolate chip, so my probability of it being a chocolate chip is going to be my denominator. That is this whole subspace over here. And then given that, so both jar A and chocolate chip, we can go and run that line and we can see that it was 1/4. So I have a 1 in 3 chance that it came from jar A. Okay. So this is kind of how conditional probability works. It takes our entire sample space, it reduces it to a given, so it's now a subspace. So our subspace it came from this chocolate chip cookie. Then my new part is going to be where both of those have occurred. So both jar A and that chocolate chip, which just ran along this line, which is 1/4, and then you can simplify your fractions. Okay, let's do another example. All right. So I have, or as of 2003, the probability of an adult in the United States having HIV or AIDS was 0.006. The Eliza test is used to detect the antibody in the blood. If the antibody is present, the test reports positive with a probability of 0.997 and a negative probability with 0.003. If the antibody is not present, the test reports a positive with a probability of 0.015 and a negative with a probability of 0.985. So I don't have, there's no data on COVID-19 yet, so otherwise that would have been a great example to be doing, but we don't have those numbers for these antibodies and tests yet. So this is another great example because we actually can see what a false positive and a a false negative as well, what those actually mean, what's the probability of those happening, and this is in 2003. So first we're going to start by drawing a tree. So the first thing that we are going to look at is whether or not we had the antibody in our blood or not. So if the antibody is present or if it's not present. So here we have a present antibody, and here is the absent antibody. Okay, so we already know the probabilities of these, so we can actually list them on our branches. So if the antibody is present, no, that's not what I want yet. Let's go and make these other branches. So it being a positive and it being a negative, we actually had, let me read this. So if the if it was present, we had I'm reading this wrong. I missed that piece. It was the 0.006. There it was. Sorry, I missed that first sentence. So the probability of someone actually having the antibody was 0.006. So the absent antibody is 0.994. Because again, these are going to add up to 1 because that's what probability is. It's either you had it or you didn't have it. So that 0.006 and that 0.994. So then if they did have the present antibody and they tested positive, that was a probability of 0.997. So the other one for negative was 0.003. The absent antibody, if it was not present, you tested positive with a 0.015 probability. So then this was 0.985 for a negative. So we wanted to see, kind of do our multiplication principle of probability. So we're going to multiply these things straight across to see what the probabilities of each of these are. So then we can answer some questions on those. So 0.006 times 0.997 gives us 0.005982. For the negative, that's 0.006 times 0.003, giving us 0.000018. Then the next one, 0.994 times 0.015, giving us 0.01491. And lastly, 0.97909. All right, so these are all the probabilities. So we have the probability that the antibody was present and you tested positive. The antibody was present and you tested negative. Absent, positive, absent, negative. So we want to see what the probability of a positive test result is. Well, to see what the probability of a positive test, I just have to add the two positive tests together. So I can add these two outcomes together and see what a positive test looks like. So a positive test, I'm going to add this 0.005982 plus 0.01491, and I get a 0.020892. So basically that's a 2% chance that you tested positive. Okay. So use the conditional probability formula to find the probability that a person with a positive test results actually had the antibody. So what we're going to be now doing is we're going to be looking at the probability of having the antibody given that you tested positive. So you took a test. Now what's the probability that you actually have it? Because these are the whole false positives, false negative things going on, which can occur. So we can do this math. So this is going to be the probability of having the antibody and testing positive over the probability of testing positive. So we just figured out the probability for testing positive. We added the two positives together. And we can see that having the antibody and testing positive was 0.005982. So we can then go and do this lovely math. And you get out 0.28, I'm just going to stop it here, 0.2863. So what that roughly means is that 28% of the time, if you tested positive, you actually had the antibody. Only 28% of the time. So that's why they do multiple different tests after certain types of weeks and whatnot, because there is a chance that even if you tested positive, it doesn't mean you actually had it. So again, this is how these conditional probabilities work. These are how your false negatives work, so forth and so on. So that means that basically 81% of the time, if you tested positive, you didn't have it. So that's a very big false negative report. Like, that's huge. But that's what they were working with back in 2003. Okay, good. So I've only been through 16 minutes, so we still have time to go through the expected value. So if you're looking at the slides that were posted, it's the last section is expected value. Alright, so expected value is one of it's very important to probability. It's also kind of hard to wrap your head around what expected value means. So expected value is basically if you know the probability of all the different outcomes, and you know what the payout is for each of those outcomes. So think about like a carnival game or something like that, where you have some chance to throw one of those rings on a bottle, and you can figure out what the payout is for you having to toss the ring, and then you actually landing on the right thing to give you the prize you want, yada yada yada. So what you do is you're going to be multiplying those probabilities times their payouts, and then you're going to add them all together. So it's the sum of all the values, so whatever positive, negative values that you have, times the respective probabilities, and what that gives you is basically a per game, so a per chance idea of what you should expect to earn or lose. So an example of that, so let's say that we want to roll a fair dice, so that means you can get 1 through 6, all equally likely to happen. If we roll a multiple of 3, we get out $3. Otherwise, we're going to lose $1. So what we're going to do is, it may be helpful if you make like a little table where you have the probability and then you have the value of that probability next to it, at least at the beginning. So we know that if we roll a multiple of 3, so that means that with the single dice, that's only going to be 3 or 6. So this is a 2 out of 6 chance of that happening, or 1/3, whatever you want to think about it as. And the value is we would earn a positive $3. On the other hand, if we rolled anything else, so that means out of these 2, that means there's only 4 other options left. So if I roll anything else, 4 out of 6, I actually am going to lose $1. So what we're going to do is we're going to multiply the probability times its value, and we're going to add everything up. So we're going to have the positive $3 times its probability of 1/3. So this is also 2/3. Plus the negative 1, because we would lose $1, losing is negative, times its probability of 2/3. And then we would add up these outcomes. So we would get out a positive 1/3. So what that means is that every time I play this game, I can expect to earn $0.33. So that means after I've played this thing 3 times, I should expect to have $1 in my pocket, which is a good thing. Like, you want positive expected values. There are basically, for the most part, everything's going to be a negative expected value because they want to earn money, whoever's trying to make these games. But if you ever see a positive expected value, play that thing. So, because you should expect to win some amount over some period of time. So each game, you should expect to win $0.33. So if you thought about it, playing 3 times, that means that I have a 1 1/3 chance of winning $3, and then 2/3 of a chance of losing $1. So that means for every 3 games, 1 of those games I should earn $3, and 2 of those games I should lose $1. So that means 3 minus 2 gives you that 1. So it's kind of a way to think about it. So for a game to be considered to be fair, so for something to be considered fair, the expected value needs to equal 0. So for something to be fair, it needs to equal $0. That way that you shouldn't expect to win or you shouldn't expect to lose any money in the long term. So if you played like 1,000 games, you're basically looking at, hey, I've done nothing. I'm at the same place I started with. So that's a fair game. Alright, so some more examples of this. So Gladys has a personal rule never to enter the lottery until the payoff reaches $4 million. When it does reach $4 million, she always buys 10 different $1 tickets. We want to figure out what the expected value of the game is. So there should be more information on that. Let's say that there are 46 numbers and you have to pick 5 of them or something like that to win. So we want to try to figure out what the actual outcome is. So we can do this. So at the beginning, we know that the probability of winning is going to be extremely low. Because again, there's only 1 ticket that is going to win. And to figure out the denominator, so the sample space, it's going to be 46, choose 5, because we don't care about the order of those numbers on the ticket. We just care that they came out to be the exact same numbers. So that gives us a probability of 1 over 1,370,754, and our winning on that one. So she has to buy a ticket. So she has to purchase the ticket to win the $4 million. So she didn't win $4 million. She actually won $3,999,999 because she still had to purchase that first ticket. So you have to think about that as well. So on the last one, it was either you won or you lost. So this time, though, it was you win this amount of money, but you have to pay for that ticket. So her winning is actually going to be $3,999,999. So if we lost, so the chance of losing is going to be the exact opposite of this number. So it's going to be 1370753 over, and you are going to lose $1 every one of these other outcomes. So out of these 1,370,753 other chances, you're going to lose $1. Well, 1, you're going to win 3,999,999, which seems nice, but we'll see. So we want to see what her expected value is. So this is for a single game right here. So we can do that. We can take that 3,999,999, multiply it by 1 over 1370754. Add that to us losing $1 for every other one. Now let's see what our outcome is. So, you can expect to lose basically $7 every time you play, which doesn't make sense because we only paid $1, but you should expect, so basically what that's telling you is that you are hardly going to win any kind of money. So every time you play once, it's like losing 7 times. Like, that's what's going on here. We're hardly winning any kind of money here. So just so you kind of understand, I did last year, so these numbers may have changed since last year, but for the Mega Millions in Georgia, for it to be considered a fair game, so for this expected value to hit 0, and I calculated it with all of the even small winnings. So like if you got like 3 numbers, you get $1 or something like that. So with all of that probability, the jackpot would need to be 505,442,681.70 for it to be considered a fair game. So that means that, so you also have to understand, you would be the only one playing because otherwise you would split the cost with some of those other people winning for the jackpot. But the jackpot would need to be $500 million in order for this to be considered a fair game. Don't play the lottery. Do not play the lottery. So, and that's again without it having to be split, because if it gets split multiple different ways, because it typically does, because the higher it is, the more people play, so the more likely it's going to get split, this is not a great outcome. So your expected value is going to be, so you just have to think about the probability times the actual value and how much you're going to lose for every single ticket as well. You multiply that probability with its value and you add up all the different outcomes, because there could be multiple different outcomes. So like for this example, I think there were like 15 or something different outcomes based off of how the numbers were arranged, yada yada yada. But that is, so Amari, that's where this is. So the 46 choose 5 was that 13. Um, 1,370,754. All right. Again, hit my 30-minute mark. You guys, so do both the conditional probability and the expected value homework. I'm going to change the website up, but it's just 1 through 6. If you want more practice, you're more than welcome to do the other ones, but just 1 through 6 of each of those different packets. If you have any questions, please don't hesitate to message me, and I will get back to you with that. You know I'm there to help you. So I'm going to look to see if there are any more questions. Otherwise, have a good weekend.